Alright guys, section 11.3 deals with our first section with angles in relation to a circle. So the first set of angles, the first category that we talk about is what we call inscribed angles. Okay, so we've given you a circle here at the top, and what we're going to do is we're going to draw two chords that have a common endpoint. Basically, we're drawing what's written down here to describe what an inscribed angle is. We're also going to give you a visual of that. So we'll put a point right here. This is going to be that common endpoint that is referred to down here. We're going to draw two chords. There will be one chord, and sure enough, here is another chord. Okay. And as you see below, it says that an inscribed angle is an angle formed by two chords with a common endpoint. That means this angle here would be classified as an inscribed angle. Okay. Then if you notice, when we drew the two chords, or now that we see the two chords drawn, what happened is this chord and this chord basically split the exterior of the circle, or split the circle, into what we would call this inscribed angle's intercepted arc. Okay, so if we follow along the two chords that formed the inscribed angle, between the other endpoints of the chord, not the common one, between this endpoint and this endpoint, we would call that the intercepted arc. Now, this chapter, I highly suggest picking up maybe some highlighters or maybe even some markers. Okay, this would be the intercepted arc. Basically, to figure out what that is or where that is, we just trace out the chords and see that we have created this intercepted arc. Intercepted meaning cut out from something else. All right. We have a theorem. The measure of an inscribed angle is half the measure of its intercepted arc. One of the most important theorems that we will learn during chapter 11. Okay. Remember, each arc has a measure in degrees, and that measure in degrees is something between 0 and 360, because the measure of an arc in degrees very simply represents what portion of the outside of the circle we have. Okay, basically if this arc was 60 degrees, 60 out of 360, this would represent 1/6 of the circle. Okay, and what we have here is a theorem. Okay, whatever the measure of this arc is, the angle would be half that. So if I told you that this arc that's highlighted in blue had a measure of 100 degrees, half of that would be 50. This angle measure would have to be 50 degrees. Okay. Vice versa, maybe I tell you that this inscribed angle has a measure of 40 degrees, multiply that by 2, and the arc would have a measure of 80 degrees. So you can kind of work with it both forwards and backwards, as we're going to see in example 1 below. Example 1 says find the values of A and B. Okay, and here's where these colors are going to come in handy. All right, A is representing the degrees, or the measure, of that arc there. All right, now that I've highlighted that, let's take the endpoints of the two arcs, or of the arc, the two endpoints, and I'm going to kind of follow that chord to where I can easily figure out or trace out which inscribed angle of all the angles shown is going with this intercepted arc. Okay, so if you can see, when we trace it out, this 60-degree inscribed angle matches up with this intercepted arc, and now we just use our theorem. It says the angle is half of the arc. Well, if this angle is half of this arc, then A must be 120 degrees. Okay, basically 60 times 2. Angle, half the measure of the arc. All right. Now, we can also work with this with the angle first. All right, now I'm looking for the angle. Okay, here's the angle. I'm going to, again, trace it out. I'm going to use a different color this time because we're going to catch a couple different arcs here. So here is the vertex of that angle. I'm going to follow the chord over here. I'm going to follow the chord over here. And then I'm going to take the endpoints of those chords, and I'm going to trace out my intercepted arc. So whatever the measure of this now green arc is, this inscribed angle will be half of that. So, what is the measure of this arc? Well, it's made up of two different pieces. The A piece, which we know is 120, and then this 30 degrees. So 120 plus 30 equals 150. And then this angle, based on our theorem here, would be half of that. And B would be 75. And we're done. Okay. Using the circle in example 1, find the measure of PQR if arc RS was 60 degrees. Okay, PQR. Arc RS. All right, I have one more color marker here. I have blue. All right, so different type of problem. Arc RS is 60 degrees. Given information. Sounds good. Angle PQR. Here's Q. I'm going to trace out angle PQR. There it is, right there, that big angle. 60 is part of it. And then I'm going to trace out in blue that whole intercepted arc from the end point of the chord to the end point of the chord. All right, well, 120 plus 30 plus 60 is 210 degrees. That's the measure of this blue intercepted arc. So then PQR, this whole angle here, would have to be half of that, 105 degrees. That would also make this little piece here 45, in case we were asked about it or were wondering. All right, let's turn the page. Find the measure of the numbered angle. Okay, let's do it. Same thing. Here's the numbered angle. There's the endpoints of the chord. All right, so where is my intercepted arc? Here it is. Well, this is an interesting question. I don't have the degree measure of that part of the intercepted arc. I kind of need it to find angle 1. Angle 1 is going to be half of the measure of this arc. How might we maybe pause this real quick, think about how we might be able to find the measure of this intercepted arc, and then replay it, and I'll tell you. Okay. This circle here means this is the center of the circle, making this a diameter, making this exactly half of a circle. How many degrees are in half of a circle? 180 degrees total. So this blue intercepted arc is 180 degrees. 180 divided by 2, and the measure of angle 1 is 90 degrees. This piece here would be 140. 140 plus 40 gives me that half of a circle. Okay, now that being said, that gets us to a theorem. An angle inscribed in a semicircle is a right angle. For that reason exactly. We kind of figured that out. This is a little bit of a theorem that draws a conclusion from what we just figured out. If this angle is inscribed in a semicircle, that means its intercepted arc would have to be 180, and 180 divided by 2 always a right angle. Let's take a look at B. Find the measure of the numbered angle. Okay. Well, here is my inscribed angle. Looks like this would be the intercepted arc. We don't have that yet. We're going to. The other piece of information given here is that this angle is 38 degrees. What do we notice about the intercepted arcs of those two angles? They're the same. All right, angle, half of arc. 38 times 2, 76 degrees. Angle, half of intercepted arc. 76 divided by 2, the measure of angle 2 is 38 degrees. It just so happens to be exactly the same as this one, which should make a whole lot of sense. If this angle and this angle have the same intercepted arc, and each degree measure will be half of whatever that is, how could these be different? They can't. And that's our second theorem that we get. Two angles, inscribed angles, with the same intercepted arc are congruent. Have to be. Just saw it right there. Okay. Also, one that we'll give you and then work with, opposite angles of a quadrilateral inscribed in a circle are supplementary. This is a theorem that a lot of students forget, and if you forget this, it would be impossible for you to do example 4. Okay. Example 4 says find the measure of angle C. This is a four-sided figure inscribed in a circle. Remember, if a shape or a polygon is inscribed in a circle, it means all of the vertices lie on the circle. In this case, all 4 of them. They give us one angle measure, 65 degrees. We're told that opposite angles of a quadrilateral inscribed in a circle are supplementary. B and D are supplementary. A and C are supplementary. So, A and C are opposite angles. 180 minus 65 would equal 115 degrees. Another way of thinking about this, 65, and then these two would have to add up to 180. 180 plus 65 is 245. We know that a quadrilateral adds up to 360 degrees, and 360 degrees minus 245 again is 115. Okay. And then lastly, we talk about a quick other theorem. This theorem is important, but once we make our conclusion, it's going to be very similar to what we talked about here. The measure of an angle formed by a tangent and a chord, different than two chords. Tangent, chord. What we want to do is make sure that we understand that we still think of intercepted arcs, and the intercepted arc would be, again, from really the point of tangency, or the endpoints of the chord. The endpoint of one chord, point of tangency between the tangent line and the circle, however you guys really want to think about that. That's perfectly fine. Okay. All right. So this would be the intercepted arc. All right. Technically, we don't call this an inscribed angle. The inscribed angle is reserved for when two chords meet. Okay, but it's still half the measure of the intercepted arc. So what we're going to do is make a little conclusion here that we'll get to probably in a little more detail next week. All right. The vertex of this angle here, that's C. Let's check out all these other angles. Vertex of the angle we were looking for. Here it is. Vertex here. Vertex here. Vertex here. All of these vertices are in the same place in relation to the circle. Where are they? The vertices of each one of the angles that we're talking about in section 11.3, whether they're formed by two chords or a tangent in a chord, the vertex of that angle is on the circle. When in angles, vertex lies on the circle, it measures half of the intercepted arc. And here's the deal. This way, we're drawing a general conclusion instead of thinking of two chords meeting in an inscribed angle versus a tangent and a chord meeting, not technically called an inscribed angle. But the thing is, if we find its measure exactly the same way, and the terminology is the same, intercepted arc, okay, why wouldn't we think of it the same? So we lump these two types of situations, two chords, and then tangent and chord, in terms of their angles, we lump them into angles whose vertex is on the circle. All right. So the first thing you'll do once we get a little deeper in this chapter, if we're working with angles and arcs, you're going to ask yourself, where is the vertex of this angle? If it happens to be on the circle, you'll know how the angle and its arc relate to each other. Angle being half of the intercepted arc. And that's it.